Good morning, students. I am Dr. Suparna Rudrahori, Assistant Professor, Department of Chemistry, Brainware University. Today I shall discuss about equation of state. Now, what is equation of state? The equation of state is mathematical expression that relates the pressure, volume, and temperature of a system, often used to describe gases. The ideal gas law, also called general gas equation, is the equation of state of a hypothetical ideal gas. Now, what is ideal gas? We all are familiar with this term ideal gas. Ideal gas are that type of gases which follow the ideal gas equation. Now, what is ideal gas equation? Ideal gas equation is PV equal to nRT, where P is the pressure, V is the volume, N is the mole number, R universal gas constant, and T is the temperature. In reality, there is no ideal gas. All gases are real gas, but at very low pressure and high temperature, real gases behave like ideal gas. Now, for ideal gas, there are some assumptions. First one is there is no intermolecular forces present in ideal gas molecules. Secondly, the ideal gas molecules have negligible volume. Actually, they are considered as point masses. And number three, the collisions between the ideal gas molecules are perfectly elastic in nature. Now, what is the difference between ideal gas and real gas? In this picture, you can see that this is the picture of an ideal gas and this is the picture of a real gas. Now, in case of ideal gas, the molecules are far apart from each other. So, the force of attraction or repulsion among the molecules are almost negligible. But in real gas, attraction force or repulsion force, we cannot neglect them. These are significant. So this is the basic difference between ideal gas and real gas. Now this is a table for difference between ideal gas and real gas. Number 1 point, molecular volume. As I have already said that ideal gas molecules have negligible volume. That means they are considered as point mass. But in real gas, the gas molecules cannot be considered as point mass. They have finite volume. Secondly, intermolecular forces. In case of ideal gas, no attractive or repulsive force present. But in real gas, some attractive and repulsive force exist. Now, ideal gas always follow PV equal to nRT equation. But real gas cannot follow the equation PV equal to nRT. Now, compressibility factor. What is compressibility factor? Compressibility factor is the ratio of molar volume of ideal gas and molar volume of real gas. Actually, for ideal gas, this compressibility factor Z is equal to 1. But in case of real gas, this compressibility factor Z is not equal to 1. It may be greater than 1 or may be less than 1. In the upcoming section, I shall discuss more about compressibility factor. Now the next point is liquefaction. Ideal gas cannot be liquefied only by applying pressure. For example, hydrogen at very low pressure and high temperature acts as ideal gas. And there are some examples of real gas: carbon dioxide, ammonia, water vapor, etc. So this is the basic difference between ideal gas and real gas. Next, what is van der Waals equation and how it is different from the ideal gas law? We all know that what is the ideal gas equation. This is our ideal gas equation. PV equal to nRT. Now in this picture you can see that this is the ideal gas situation and this is the real gas situation. As we have already discussed that in case of ideal gas there is no attraction and repulsion force among the molecules, but we cannot neglect the attraction force or repulsion force present in the real gas molecules. So we have to correct the pressure term as well as volume term in this ideal gas equation. Now what is pressure correction? The existence of intermolecular forces between the molecules lowers the observed pressure in real gases because the molecules are attracted to each other. So the pressure on the container will be less than the ideal gas. Hence, the internal pressure of the real gas is higher than that of ideal gas. Now, if I consider the internal pressure of the real gas is P prime and the internal pressure of ideal gas is P, P prime is always greater than P. Now here, the attraction or repulsion force occurs between two nearby molecules. So the corrected pressure term P prime will be P plus A into N by V whole square, where A is constant and N by V means the number of molecules per liter. Actually V is the volume and N is the whole number, and the square terms arises here due to that attraction or repulsion force arises between two molecules, so that these square terms appears here. The next one is volume correction term. As we have already discussed that in ideal gas molecules are actually point masses, so they don't have any significant volume, but in real gas the gas molecules have finite volume, so we need to correct the volume term. So if I say the ideal gas volume is V and the real gas volume is V prime, now V prime is equal to V minus NB, where B is the constant which indicate the molecular volume and that differs for each gases. Now after putting the volume correction term as well as pressure correction term, the ideal gas equation turns into this new equation which is known as van der Waals gas equation, where the equation is P plus A n square by V square into V minus NB equal to nRT. This is known as van der Waals gas equation or real gas equation. Now, how can we determine the unit of these two constants A and B? In this van der Waals equation, the corrected pressure term is A into n square divided by V square. So this term has the unit equal to the unit of pressure. So A n square divided by V square has the unit of atmosphere. So the unit of A is equal to unit of pressure into unit of V square divided by unit of nr square. So the unit of A is atmosphere into liter square into mole to the power minus 2. Similarly, the unit of B. Now this is the volume correction term NB. So NB has the unit of volume. So NB is unit of volume, so the unit of B is liter per mole. Now one important question arises here: when real gas behaves ideally? Actually, at low pressure and high temperature, real gas behaves ideally. Why? Because at low pressure and very high temperature, volume becomes infinite. If this term becomes infinite, the total pressure correction term will be near equal to 0. Similarly, if V is very high, then NB is uh, very negligible term. So V minus NB is almost near equal to V. So this van der Waal equation then turns into PV equal to nRT. So we may say that at very low pressure and high temperature, the real gas behaves ideally. Now a very important thing, which is critical phenomena of gas. Now what is critical phenomena? Critical phenomena in real gas describe the behavior of gases at their critical point, where the distinction between liquid and vapor phases disappears. Now what is critical point? What is the behavior of this point? At the critical point, the density of gas and liquid phase becomes equal, and there is no distinct phase boundary between the liquid phase and the gas phase. Properties like heat capacity, compressibility, density show large fluctuations here. So in this picture you can see pressure versus volume versus temperature plot, and above the critical temperature all the component becomes gas. Now what is critical temperature? Critical temperature is considered as the highest temperature at which a gas can be liquefied regardless of pressure. Now what is critical pressure? The minimum pressure required to liquefy a gas at its critical temperature. What is critical volume? The volume occupied by 1 mole of substance at its critical point. This is critical volume. Now the relation between van der Waal gas constants and critical phenomena. For n mole real gas, the van der Waal equation is this, as I have already discussed. Now, for 1 mole gas at the critical point, dP/dV at constant temperature and the double derivative term of this dP/dV both are equal to 0. So we can write the dP/dV at constant temperature is equal to 0, and the second derivative is also equal to 0 at that critical point. Now this equation 1 and equation 2 becomes this equation 3. By using equation 1 and equation 2, we can write this equation, and from these two equations 3 and 4 we may write Vc equal to 3b. Here C term is for critical point. So at that critical point the volume Vc is equal to 3b. Tc is the critical temperature and Pc is the critical pressure. Now at the critical point the compressibility factor can be calculated like that: Zc equal to PCVC divided by R into Tc, which is equal to 3 by 8. By putting these three values here, 3 by 8, which is equal to 0.375. Now I can discuss the compressibility factor elaborately. Now what is compressibility factor? Compressibility factor is the measure of how much real gas derives from real gas deviates from the ideal gas behavior. It is defined as the ratio of the molar volume of real gas to the molar volume of an ideal gas at the same temperature and pressure. So this is our Z, compressibility factor, which is equal to V real, that means volume of real gas, divided by V ideal, that means molar volume of ideal gas. Now for ideal gas, this Z equal to 1. But for real gas, Z is not equal to 1. It may be less than 1, may be greater than 1. If it is less than 1, that means V real is less than V ideal. That means volume of real gas is lower than the volume of ideal gas. That means there are some attraction force between the gas molecules. So if Z less than 1, gas shows greater compressibility due to attractive force. Similarly, if Z greater than 1, that means real gas volume is greater than ideal gas volume. So it means that gas shows less compressibility due to repulsion force. This is Z versus pressure term. For ideal gas, Z is equal to 1. This is the curve for nitrogen, hydrogen and helium, and this is for methane, and this is for carbon dioxide. Now we shall discuss some question answer. Number 1 question: why do real gas deviates from ideal gas? Because in case of ideal gas, we have taken some assumptions. Number 1 assumption was there are no attraction forces or repulsion forces among the gas molecules. And secondly, all the collisions between them is perfectly elastic in nature, and the volume of the ideal gas molecule is considered as negligible volume. But in reality, intermolecular forces are present in case of real gas, so that real gas deviates from ideal behavior. Second question: what are the correction introduced in Van der Waals equation? I have already discussed about it. This is our Van der Waals equation, and this is our pressure correction term due to presence of attraction or repulsion forces among the real gas molecules, and this is the volume correction term because the real gas molecules have significant volume or finite volume. So this is our volume correction term NB. So this is our Van der Waals gas equation for real gases. Now there are more practice questions. I can explain the answers one by one. First question: what is the equation of state for an ideal gas? You all know PV equal to nRT. Now the second one: list up to assumptions made in derivation of the ideal gas law. I have said many times. So number 3: why do real gases deviate from ideal behavior at high pressure? At high pressure means when we increase the pressure, volume become decrease, so the molecules will come closer. So the attraction force or repulsion force, that means intermolecular force among the molecules, will increase. So the real gas deviate from the ideal behavior at high pressure. Now number 4 question: what do the constant A and B in Van der Waals equation present? A is due to pressure correction term, B is for the volume correction term. You all know that. Now fifth question: what is the significance of compressibility factor Z? Compressibility factor Z is nothing but how the real gas deviates from ideal gas. Now Z is equal to the ratio of molar volume of real gas and ideal gas. Number 6: under what condition does a real gas behave most like an ideal gas? The answer is very easy: when the pressure is very less and temperature is very high. That means the volume become large, and then the real gas behaves like ideal gas. What is the critical point? Critical point means above that point the any gas behaves like gas and they cannot be liquefied only by applying pressure. And I have already discussed critical temperature, critical volume and critical pressure at that point. Now the eighth question, how is the van der Waals equation more accurate than the ideal gas equation? Yes, van der Waals gas equation is more accurate because here we can consider the intermolecular forces among the molecules, and the molecules, we cannot consider the molecule as point mass because molecules, though they have very tiny, but they have some finite volume. So van der Waals equation is more accurate. Now number 9 question, state the unit of van der Waals constant A. I have already showed it. Now number 10, explain why liquefaction of gas is not possible above the critical temperature. Actually, above the critical temperature, the kinetic energy of the gas molecules becomes very large. So we cannot liquefy them by only applying pressure. So this is whole about equation of state. So it is our total syllabus of equation of state. Now thank you very much guys.